What was the first robot you built under the flag of Boston Dynamics? Big Dog?
Well, there was the Ivo runner, but it wasn't even a whole robot. It was just legs that we took off the legs on Ibos and attached legs we'd made, and we got that working and showed it to the Sony people. We worked pretty closely with Sony in those years. One of the interesting things is that it was before the internet and Zoom and anything like that.
Mhm.
So we had 6 ISDN lines installed, and we would have a telecon every week that worked at very low frame rate, something like 10 hertz. English across the boundary with Japan was a challenge, trying to understand what each of us was saying and have meetings every week for several years doing that. And it was a pleasure working with them. They were really supporters. They seemed to like us and what we were doing. That was the real transition from us being a simulation company into being a robotics company again.
It was a quadruped. The legs were four
Yeah.
legs or 2 legs?
Yeah, no, 4 legs. Yeah.
And what did you learn from that experience of building basically a fast moving quadruped?
Mostly we learned that something that small doesn't look very exciting when it's running. It's like it's scampering, and you had to watch a slow-mo for it to look like it was interesting. If you watch it fast, it was just like
That's funny.
One of my things was to show stuff in video, even
Yeah.
from the very early days of the hopping machines. And so I was always focused on how's this going to look through the viewfinder, and running IBO didn't look so cool through the viewfinder.
So what came next in terms of what was a big next milestone in terms of a robot you built?
I mean, you got to say that Big Dog was, sort of put us on the map and got our heads really pulled together. We scaled up the company. Big Dog was the result of Alan Rudolph at DARPA starting a biodynamics program. And he put out a request for proposals. And I think there were 42 proposals written and 3 got funded. One was Big Dog. One was a climbing robot, Rise. And, that put things in motion. We hired Martin Buehler. He was a professor in Montreal at McGill. He was incredibly important for getting Big Dog out of the lab and into the mud, which is was a key step to really be willing to go out there and build it, break it, fix it, which is sort of one of our mottos at the company.
So testing it in the real world.
Testing.
People who don't know, Big Dog, maybe you can correct me, but it's a big quadruped, 4-leg robot. That it looks big, could probably carry a lot of weight. Not the most weight that Boston Dynamics have built, but a lot.
Well, it's the first thing that worked. So let's see. If we go back to the leg lab, we built a quadruped that could do many of the things that Big Dog did, but it had a hydraulic pump sitting in the room with hoses connected to the robot. It had a VAX computer in the next room. It needed its own room because it was this giant thing with air conditioning, and it had this very complicated bus connected to the robot. And the robot itself just had the actuators. It had gyroscopes for sensing and some other sensors, but all the power and computing was off board. Big Dog had all that stuff integrated on the platform. It had a gasoline engine for power, which was a very complicated thing to undertake. It had to convert the rotation of the engine into hydraulic power, which is how we actuated it. So there was a lot of learning just on the building the physical robot and the system integration for that. And then there was the controls of it.
So for Big Dog, you brought it all together onto one platform,
right?
And then so you
could take it out in the woods.
Yeah, and you did.
We did. We spent a lot of time down at the Marine Corps base in Quantico, where there was a trail called the Guadalcanal Trail, and our milestone that DARPA had specified was that we could go on this one particular trail that involved, a lot of challenge. And we spent a lot of time. Our team spent a lot of time down there. Hiking. Those were fun days.
Hiking with the robot. So what did you learn about like what it takes to balance a robot like that on a trail, on a hiking trail in the woods? But basically, forget the woods, just the real world. That's the big leap into testing in the real world.
Yeah. As challenging as the woods were, working inside of a home or in an office is really harder.
Yeah.
Because when you're in the woods, you can actually take any path up the hill. All you have to do is avoid the obstacles. There's no such thing as damaging the woods, at least, to first order. Whereas if you're in a house, you can't leave scuff marks. You can't bang into the walls. The robots aren't very comfortable bumping into the walls, especially in the early days. So I think those were actually bigger challenges once we faced them. It was mostly, getting the systems to work well enough together, the hardware systems to work, and the controls. In those days, we did have a human operator who did all the visual perception going up the Guadalcanal Trail. So there was an operator who was right there, who was very skilled at, even though the robot was balancing itself and placing its own feet, if the operator didn't do the right thing, it wouldn't go. But years later, we went back with one of the precursor to Spot, and we had advanced the controls and everything so much that an complete amateur, could operate the robot the first time up and down, whereas it had taken us years to get there in the previous robot.
So if you fast forward, Big Dog eventually became Spot.
So Big Dog became LS3, which is the big load carrying one.
Just a quick pause. It can carry 400 pounds.
It was designed to carry 400, but we had it carrying about 1,000 pounds once.
Of course you did. Just to make sure.
We had one carrying the other one. We had two of them. So we had one carrying the other one. There's a little clip of that. We should put that out somewhere. Yeah. That's from like 20 years ago. But.
Wow. And it can go for very long distances. It can travel 20 miles.
Yeah. Gasoline,
yeah. And that eventually just, okay, sorry. So LS3, then what? How did that lead to Spot?
So Big Dog and LS3 had engine power and hydraulic actuation. Then we made a robot that was electric power. So there's a battery driving a motor, driving a pump, but still hydraulic actuation.
Mm-hmm. Yeah.
Larry sort of asked us, could you make something that weighed 60 pounds that would not be so intimidating if you had it in a house where there were people? And that was the inspiration behind the Spot, pretty much as it exists today. We did a prototype the same size. That was the first all-electric, non-hydraulic robot.
What was the conversation with Larry Page like about? So here's a guy that kind of is very product focused and can see a vision for like what the future holds. That's just interesting kind of aside. What was the brainstorm about the future of robotics with him like?
I mean, it was almost as simple as what I just said. We were having
make it smaller?
Meeting. He said, "Yeah, geez, do you think you could make a smaller one that wouldn't be so intimidating? Well, like a big dog,
yeah.
If it was in your house." And I said, "Yeah, we could do that." And we started and did.
Is there a lot of technical challenges to go from hydraulic to electric?
I had been in love with hydraulics and still love hydraulics. It's a great technology. It's too bad that somehow the world out there looks at it like it's old fashioned or that it's icky. And it's true that it is very hard to keep it from having some amount of dripping from time to time. But if you look at the performance, how strong you can get in a lightweight package. And of course, we did a huge amount of innovation. Most of hydraulic control, that is the valve that controls the flow of oil, had been designed in the 50s for airplanes. Mm-hmm. It had been made robust enough, safe enough that you could count on it so that humans could fly in airplanes. And very little innovation had happened. That might not be fair to the people who make the valves. I'm sure that they did innovate, but the basic design had stayed the same. And there was so much more you could do. And so our engineers designed valves, the ones that are in Atlas, for instance, that had new kinds of circuits. They sort of did some of the computing that could get you much more efficient use. They were much smaller and lighter so that the whole robot could be smaller and lighter. We made a hydraulic power supply that had a bunch of components integrated in this tiny package. It's about this big, the size of a football. It weighs 5 kilograms and it produces 5 kilowatts of power. Of course, it has to have a battery operating, but it's got a motor, a pump, filters, heat exchanger to keep it cool, some valves, all in this tiny little package. So hydraulics, could still have a ways to go.
one of the things that stands out about the robots Boston Dynamics have created is how beautiful the movement is, how natural the walking is, and running is, even flipping is, throwing is. So maybe you can talk about what's involved in making it look natural.
Well, I think having good hardware is part of the story, and people who think you don't need to innovate hardware anymore are wrong, in my opinion. So I think one of the things, certainly in the early years for me, taking a dynamic approach where you think about what's the evolution of the motion of the thing going to be in the future, and having a prediction of that that's used at the time that you're giving signals to it, as opposed to it all being servoing, which is servoing is sort of backward looking. It says, okay, where am I now? I'm gonna try and adjust for that. But you really need to think about what's coming.
So how far ahead do you have to look in time?
It's interesting. I think that the number is only a couple of seconds for spot. So there's a limited horizon type approach where you're recalculating, assuming what's going to happen in the next second or second and a half. And then you keep iterating, at the next, even though a tenth of a second later, you'll say, okay, let's do that again and see what's happening. And you're looking at what the obstacles are, where the feet are going to be placed, how to, you have to coordinate a lot of things if you have obstacles and you're balancing at the same time. And it's that limited horizon type calculation that's doing a lot of that. But if you're doing something like a somersault, you're looking out a lot further, right? If you want to stick the landing, you have to get you have to, at the time of launch, have, momentum and rotation, all those things coordinated so that a landing is within reach.
How hard is it to stick a landing? I mean, that's very much under actuated. Like once you've in the air, you don't have as much control about anything. So how hard is it to get that to work? You first of all did flips with a hopping robot.
If you look at the first time we ever made a robot do a somersault, it was in a planar robot. It had a boom. So it was restricted to the surface of a sphere. We call that planar. So it could move fore and aft, it could go up and down, and it could rotate. And so the calculation of what you need to do to stick a landing isn't all that complicated. You have to look at, you have to get time to make the rotation. So how hard you jump, how high you jump gives you time. You look at how quickly you can rotate. And so, if you get those two right, then when you land, you have the feet in the right place. And you have to get rid of all that rotational and linear momentum. But, that's not too hard to figure out. And we made, back in about 1985 or 6, I can't remember, we had a simple robot doing somersaults. To do it in 3D, really the calculation is the same. You just have to be balancing in the other degrees of freedom. If you're just doing a somersault, it's just a planar thing. Rob was my graduate student, and we were at MIT, which is when we made, a two-legged robot do a 3D somersault for the first time. In order to get enough rotation rate, you needed to do tucking also. Withdraw the legs in order to accelerate it. And he did some really fascinating work on how you stabilize more complicated maneuvers. You remember he was a gymnast, a champion gymnast before he'd come to me. So he had the physical abilities, and he was an engineer, so he could translate some of that into the math and the algorithms that you need to do that.
He knew how humans do it. You just had to get robots to do the same.
Unfortunately, though, humans don't really know how they do it.
Yeah.
Right? We're coached. Right. We have ways of learning, but do we really understand in a physics way what we're doing? Probably most gymnasts and athletes don't know.
So in some way, by building robots, you are in part understanding how humans do, like walking. Most of us walk without considering how we walk, really.
Right.
And how we make it so natural and efficient, all those kinds of things.
Atlas still doesn't walk like a person, and it still doesn't walk quite as gracefully as a person, even though it's been getting closer and closer. The running might be close to a human, but the walking is still a challenge.
That's interesting, right? That running is closer to a human. It just shows that the more aggressive and kind of the more you leap into the unknown, the more natural it is. I mean, walking is kind of falling always, right?
And something weird about the knee, that you can kind of do this folding and unfolding and get it to work out a human can get it to work out just right. There's compliances. Compliance means springiness in the design that are important to how it all works. Well, we used to have a motto at Boston Dynamics in the early days, which was you have to run before you can walk.
That's a good motto, because you also had Wildcat, which was one of the along the way towards Spot, which is a quadruped that went 19 miles an hour on flat terrain. Is that the fastest you've ever built?
Oh, yeah.
Might be the fastest quadruped in the world. I don't know.
For a quadruped, probably. Of course, it was probably the loudest, too. So we had this little racing go-kart engine on it. And we would get people from, 3 buildings away sending us, complaining about how loud it was.
So at the Leg Lab, I believe most of the robots didn't have knees. How do you figure out what is the right number of actuators? What are the joints to have? What do you need to have? We humans have knees and all kinds of interesting stuff on the feet. The toe is an important part, I guess, for humans. Or maybe it's not. I injured my toe recently, and it made running very unpleasant. Mm-hmm. So that seems to be kind of important. Mm-hmm. So how do you figure out, for efficiency, for function, for aesthetics, how many joints to have, how many actuators to have?
Well, it's always a balance between wanting to get where you really want to get and what's practical to do based on your resources or what you know and all that. So, the whole idea of the pogo stick was to do a simplification. Obviously, it didn't look like a human. I think a technical scientist could appreciate that we were capturing some of the things that are important in human locomotion without it looking like it, without having a knee and ankle. I'll tell you the first sketch that Ben Brown made when we were talking about building this thing was a very complicated thing with zillions of springs, lots of joints. It looked much more like a kangaroo or an ostrich or something like that, things we were paying a lot of attention to at the time. So my job was to say, okay, well, let's do something simpler to get started, and maybe we'll get there at some point.
I just love the idea that you two were studying kangaroos and ostriches.
Oh yeah, we did. We filmed and digitized data from horses. I did a dissection of a ostrich at one point, which has absolutely remarkable legs.
Dumb question: do ostriches have a lot of musculature on the legs, or no?
Most of it's up in the feathers, but there's a huge amount going on in the feathers, including a knee joint. The knee joint's way up there. The thing that's halfway down the leg that looks like a backwards knee is actually the ankle. The thing on the ground, which looks like the foot, is actually the toes. It's an extended toe.
Fascinating.
But the basic morphology is the same in all these animals.
What do you think is the most beautiful movement of an animal? Like, what animal you think is the coolest? Land animal. Let's go. Because fish is pretty cool. Like the way fish moves to water, but legged locomotion.
The slow-mos of cheetahs running are incredible. There's so much back motion and grace, and of course they're moving very fast. The animals running away from the cheetah are pretty exciting. The pronghorn, which they do this all 4 legs at once jump called a pronk to kind of confuse especially if there's a group of them, to confuse whoever's chasing them.
So they do like a misdirection type of thing?
Yep, they do a misdirection thing. The front-on views of the cheetahs running fast, where the tail is whipping around to help in the turns, to help stabilize in the turns. That's pretty exciting.
Because they spend a lot of time in the air, I guess, as they're running that fast.
But they also turn very fast.
Is that a tail thing, or is that do you have to have contact with the ground?
Everything in the body is probably helping turn, because they're chasing something that's trying to get away that's also zigzagging around. But I would be remiss if I didn't say, humans are pretty pretty good too. You watch gymnasts, especially these days, they're doing just incredible stuff.
Well, especially Olympic level gymnasts. See, but there could be cheetahs that are Olympic level. We might be watching the average cheetah versus there could be a really special cheetah that can do
You're right.
When did the knees first come into play in you building legged robots?
In Big Dog.
Big Dog.
Yeah, Big Dog came first, and then Little Dog was later. And there's a big compromise there. Human knees have multiple muscles, and you could argue that there's, it's a technical thing about negative work. When you're contracting a joint, but you're pushing out, that's negative work.
Mm-hmm.
And if you don't have a place to store that, it can be very expensive to do negative work. And in Big Dog, there was no place to store negative work in the knees. But Big Dog also had pogo stick springs down below. So part of the action was to comply in a bouncing motion. Later on in Spot, we took that out. And as we got further and further away from the leg lab, we had more, energy-driven controls.
Is there something to be said about like knees that go forward versus backward?
Sure. There's this idea called passive dynamics, which says that although you can use computers and actuators to make a motion, a mechanical system can make a motion just by itself if it gets stimulated the right way. So Tad McGeer I think in the mid 80s, maybe it was in the late 80s, started to work on that. And he made this legged system that could walk down an inclined plane where the legs folded and unfolded and swung forward, do the whole walking motion, where there was no computer. There were some adjustments to the mechanics so that there were dampers and springs in some places that helped the mechanical action happen. It was essentially a mechanical computer. And the interesting idea there is that it's not all about the brain dictating to the body what the body should do. The body is a participant in the motion.
So a great design for a robot has a mechanical component where the movement is efficient even without a brain.
Yes.
How do you design that?
I think that these days most robots aren't doing that. Most robots are basically using the computer to govern the motion. Mm-hmm. Now the brain, though, is taking into account what the mechanical thing can do and how it's going to behave. Otherwise, it would have to really forcefully move everything around all the time, which probably some solutions do, but I think you end up with a more efficient and more graceful thing if you're taking into account what the machine wants to do.